So the first thing we're doing is ranking in order of increasing boiling points. So the first three here are alkanes, and with alkanes, the more branching, the less surface area that can contact another molecule, and the lower the boiling point, the lower dispersion forces. So we would rank in terms of going from lowest to highest, C, then A, then B. And then between G and F, both of those would rely on dipole-dipole intermolecular forces. The ether will have some canceling out. And the alkyl halide will have less of that. So it's likely that the ether will be lower than the alkyl halide, followed by the alcohol, which can participate in hydrogen bonding, then the carboxylic acid, which forms hydrogen bonding dimers. Okay, so this was ranked from, again, lowest boiling point to highest boiling point. The next one is ranking in order of increasing acidity. And in terms of acidic protons, the ether, hydrogens are not very acidic compared to alcohols and carboxylic acids. So we would go with the ether first. Alcohols are not as acidic as carboxylic acids. The alcohol next. In terms of the carboxylic acids, we have increased induction, which will make it more acidic due to stabilization of the corresponding conjugate base. E would be the most. Okay, in terms of review of the reactions that make carboxylic acids, we have ozonolysis. Ozonolysis of an alkyne, and we'll get carboxylic acid. This one is asymmetric, so we get two different carboxylic acids versus a symmetrical alkyne, which would produce two of the same thing. And we can oxidize primary alcohols, all with sodium dichromate, and go all the way up to the carboxylic acid. Remember that there's through an aldehyde intermediate that gets further oxidized to a carboxylic acid. We have oxidation of a secondary alcohol to a ketone, which is a bit strange to see in the review making carboxylic acid section, but they're just trying to distinguish the difference between primary and secondary alcohol and oxidation products of those. And then we have potassium permanganate. You could also use sodium dichromate here to do a benzoic oxidation, because there's at least one hydrogen in the benzoic position here. That carbon can get oxidized, whereas the tert-butyl's carbon does not have hydrogen. It does not get oxidized. We just oxidize that benzoic carbon to get carboxylic acid. So those are some review reactions, ways that you've seen carboxylic acids being made in prior chapters. And then on the next page, we have new methods to make carboxylic acids. And these are nitrile hydrolysis and forming a Grignard reagent and reacting it with carbon dioxide. Both of these, you might call them, sometimes they're called one carbon homologation reactions. Basically adding one carbon. So it's important to note that when you use these, if you start out with 3 carbons, you're going to get 4 carbons. And you can do that in each case. So you are extending the carbon backbone by using these reactions. So in terms of the nitrile hydrolysis reaction, note that we need to have a primary alkyl halide. The reason for that is because the first step is going to be an SN2 reaction, where cyanide replaces the bromine in an SN2 process. So because of that, it needs to be unhindered. Whereas for the Grignard reagent, it doesn't necessarily need to be unhindered. It could be primary, secondary, or tertiary alkyl halide. And it could even be benzene or some sp2 hybridized carbon. Okay, so there's a lot more versatility there, but you do need to not have any other acidic protons around in a Grignard reaction. Because of course it would quench the Grignard. Okay, so in this case you would need an acidic workup, even though it's not mentioned. That's where this final proton comes from. Okay, so let's look at how these reactions might be used. So we're going to be making this carboxylic acid, and we'll be starting from an alkane. So remember, whenever you start from an alkane, you need to do a radical halogenation. That's the first step. So the bromine will go into the most substituted position. And now we probably want to get the halogen over onto this carbon so we can make the carboxylic acid. So we need a series of elimination and addition reactions in order to move that halogen's position on the carbon backbone. So elimination and then addition. So to do this, you need a strong base to do an E2 reaction, followed by the addition of HBr, and then anti-Markovnikov fashion, adding the peroxide there. And then because this is primary, we can do the nitrile hydrolysis if we want. In addition, there's no acidic protons here, so we can also do the Grignard with carbon dioxide. You have your two options at this point for making the product. So you can treat this with sodium cyanide and then do acidic hydrolysis. Or we could treat this with magnesium to form the Grignard reagent, treat this with dry ice, solid carbon dioxide, and then an acidic workup. And either way, you would get the carboxylic acid product. It's drawn out. So you have either option here in this case. And the next one. So now we have the benzylic position, which needs to be functionalized. So typically you use NVS, light or heat, to put a bromine into benzylic position. And now in this case, because this is a tertiary carbon, you have to use the Grignard. So we would treat this with magnesium, followed by CO2 and then acidic workup. The next one is the same thing, but we have this attached group here, which needs to be protected. Because if we're going to be using Grignard, we need to make sure that there's no other acidic protons around. So we first need to go through a protection of the alcohol. And after we protect, now we can proceed with forming a new carbon-carbon bond. Do the same reactions that we did before. Add the bromine. Do the Grignard reaction. And then do a deprotection. And next, look at the mechanism for adding carbon dioxide as the electrophile in a Grignard reaction. So carbon dioxide like this, and the carbon is electrophilic, being attached to the oxygens. So we can show the Grignard reagent attacking the electrophilic carbon. Which would make the carboxylate. And we would need an acidic workup. To provide the proton to get to the product. We're looking next at the mechanism for the hydrolysis of a carboxylic acid to an amide. And then later we'll look at the reaction of that further to a carboxylic acid. So you can think of a carbon-nitrogen triple bond in a nitrile as kind of like a carbonyl. Right? The carbonyl has a CO double bond, and the carbon triple bonded to nitrogen has 2 pi bonds, right, instead of 1 for a carbonyl, but they're still going to be very similar. So just like a carbonyl would be protonated in the presence of an acid, a nitrile can also be protonated in the presence of an acid. The lone pair on the nitrogen, like the lone pair on the oxygen of the carbonyl, can pick up that proton. When that happens, that makes the carbon even more electrophilic. And so it can easily get attacked by even a weak nucleophile like water. Show that nucleophilic attack. So that gives us this intermediate. And notice the product here has a carbonyl. So this turns into a carbonyl. We need to lose these protons. And then this ends up as an NH2. So the goal is to get to that point. Remember that under acidic conditions, it's common to find intermediates that either have 1 positive charge or are neutral. We try to avoid 2 positive charges in these methods. So in order to do that, to avoid 2 positive charges, we're going to deprotonate first. We'll do a little proton shuffle. Deprotonate to get something neutral, and then we'll be able to reprotonate somewhere else in the molecule, and then only have 1 positive charge. This is showing the 2 resonance contributors, and this one looks a lot more like the product. And so all we need to do is do a deprotonation to get to the amide. So really, it's mostly a series of proton transfers with the nucleophilic attack of water to get from a nitrile to an amide. Label those. Easy to recognize the reaction. And then later we'll see the hydrolysis of an amide all the way to a carboxylic acid. Next part is filling in the empty boxes with the proper reagents. So to do a benzylic halogenation, yes, in either light or heat. And to convert that halogen to a carboxylic acid where this is a tertiary carbon, you cannot do the nitrile hydrolysis because this is not an unhindered alkyl halide. So instead we can use Grignard reagent and add CO2, and after an acidic workup, we would get the carboxylic acid where one additional carbon has. Next, we're looking at the reduction of a carboxylic acid all the way to a primary alcohol. We need to use our stronger reducing LAH. Or additionally, in this chapter, I believe BH3THF is but we've learned in the past that hydride will do that quite fine. And after an acidic workup, we can get the alcohol. If we want to oxidize that back to an aldehyde, we would use PCC. And then this looks like the introduction of these three carbons. Yeah, Grignard. Throwing the Grignard reagent, and after an acidic workup, we'll be able to produce the secondary alcohol. Okay, so the next problem says an attempted methanolysis of the following acid halide provided this methyl ester and an unknown compound with a molecular ion of 152. Determine the structure of the unknown. So in looking at this NMR, looks like the aromatic ring with the para substitution is evident. Doublets here in the aromatic region of around 7 to 8, each integrating for 2 hydrogens symmetry. It's like the methoxy methyl group here is evident in this hydrogen singlet, and around 4 ppm is expected due to the presence of the neighboring oxygen. And then this sort of very broad signal over here, integrating for 1 hydrogen at around 12 ppm, sometimes hard to see, is likely a carboxylic acid. So given that the NMR, very likely that we, in addition to getting some methyl ester, there was some carboxylic acid produced as well. We could check the mass of this, do a rough calculation. So we have 6 carbons in the ring, 7, 8. So 8, 12 is 96. We have how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. Plus and then how many oxygens? 3. So 3 oxygens. And that is we can do math today, 48. And let's see, so 16, 22, 11, 152. So that matches the molecular ion given. Okay, and then just looking at if it matches the carbon NMR given. So we would have the 60 to 50 to 100 range. This is likely the sp3 hybridized carbon attached to the oxygen. And then these are likely from the aromatic ring. and then this one for. Right, so this is a little out of the 0 to 150 region, but proximity to another oxygen. Shift that a little more down. Okay, so next we have a review section. Explain the stereochemistry observed in the following reaction. This one is definitely quite a bit of a review. This is an E2 reaction from last semester. You might notice that both the alpha carbon and the beta carbon are chiral centers. And so in this case, we need to draw the Newman projection to the stereochemical output of the reaction in this E2 reaction. So to draw a Newman projection, for example, you could place your eyeball to look down that carbon-carbon bond. Draw my little circle and my dot to start my Newman projection. Pointed straight down is the phenyl. Okay, and then pointed to my left is the methyl group here. The hydrogen. And that's the hydrogen we're going to be removing the elimination reaction. On the alpha carbon, which is in the back, we have the phenyl group pointed straight up and in the same plane as the other phenyl group here. On the same side as the methyl pointed back is the bromine and another hydrogen here. I always like to kind of circle the leading group, which is the halogen, and then the hydrogen attached to the beta carbon that we'll be removing in the reaction. So kind of imagine in the E2 reaction, the hydroxide is coming in to take this proton. We'll be forming a pi bond between the front carbon and the back carbon. And then we'll be leaving, this will be sort of leaving as it is. And they're already anti-periplanar, which is perfect. So we don't need to do any rotation in order to get these two groups anti. So after the reaction, there's going to be a pi bond being formed. You can kind of imagine the formation of the p orbital overlapping in the same plane as the proton transfer and the loss of the leading group. And then these groups sort of flatten out, right, because the carbon becomes sp2 in terms of planar. You can just draw the groups that are already here in the front, methyl, phenyl, back is pi bond. So drawn in a bond line structure, you might see the double bond in the two carbons, and then there's some different groups attached. So on the back carbon, there's phenyl and methyl. You can kind of draw those in. And then we just need to be careful with what's on the same side, right? So on the same side as the methyl is the phenyl. Other phenyl. Over here on the same side as the methyl. Hydrogen here on the same side as the phenyl. So we end up with the alkenes, the exclusive stereoisomer. So that's good review for the ACS exam, right? Okay, so this one is propose a mechanism for the following transformation. So one thing we know about Lewis acids is how they like to coordinate the lone pairs. We saw that in Rayleigh-Crafts reactions, the electrophilic aromatic substitution chapter. So perhaps the lone pair acts as a Lewis base and reacts with the boron as a Lewis acid and forms an acid-base complex. Draw that. This is, now kind of think of this as a proton. Right? So it is making these carbons more electrophilic and allowing them at easier reactions. It's also making this oxygen a better leaving group. Much more likely to break this bond. I'll show you why. Because what we form if we have that bond break is a resonance stabilized benzoic cation. We're able to do sort of like a loss of a leaving group there, and that ends up with the carbocation, which is resonance stabilized in benzoic. So it's fairly stable. There's two different things you could do here to get to the product. One option is a hydride shift. So if we do a hydride shift, you might be thinking, well, why would it shift if it's benzoic and resonance stabilized? Well, after the shift occurs, now it's still resonance stabilized, right? And it's going to be part of a carbon-oxygen double bond, which is also very stable. So at this point, the Lewis acid just has to leave, and we can use those electrons to form a double bond. And this would pick out the catalyst. So that's option one, right? And I'm going to call this sort of intermediate A. So I can show you another possibility for intermediate A. So from intermediate A, also possible instead of a hydride shift, is a deprotonation. So perhaps something in there, some kind of base, comes and takes this hydrogen. So essentially, and we're not really sure exactly what the base is. There's any water present or some other base. Perhaps a base comes and takes that proton. And electrons shift to form a pi bond. So think of this as a deprotonation step. That would give us an alkene. And I'll just kind of draw a proton. Maybe it's attached to a base somewhere, maybe it's floating around in solution. And perhaps it gets regioselectively added to the benzoic carbon. This is essentially like a tautomerization, moving the proton around from one position to another. So that would end up with this intermediate, which I might call intermediate B. And I'm going to need intermediate B up here. This is another possible way to get to intermediate B. So either you show a hydride shift, or you could show a deprotonation at a different position to get to B. The next question is asking, why do we get this regioisomer observed in this reaction? So this is a conjugated diene. Okay, and if you recall, we'll talk about how we always show proton transfer, which in this case is a deuterium transfer. We always show that occurring at the terminal position of the conjugated system. And that's so that we get a allylic carbocation, which is much more stable than having the carbocation here and not having it in conjugation with 5 bond. So it's regio-selective proton transfer. To generate resonance stabilized so then we could put, for example, if we had protonated or deuterated in this case, in the interior carbon, this is not resonance stabilized. So from here, the bromide that gets formed in the first step just does a nucleophilic attack to produce major lysine. Okay, the next question is regarding the Wittig reaction, which utilizes a ylide, a phosphonium ylide, and an aldehyde or ketone. So the product, if you recognize these two reactants, you should be able to come up with the product. Alkene. And this is very likely the product of this unit. We just want to recognize that this is an ylide and it's an alkene. So just kind of double checking that this is the product that we would expect. So we have the two singlets here. It says they're integrating for 1.5, but that doesn't make sense. So multiply everything by 2 in order for the integration to make sense. So these methyls over here, it would be hard to tell which one is which. Signal. And then the hydrogen here is likely to be this signal that's more downfield, 5.5. And then we have basically an ethyl group, right? But it's not quite isolated because this is a neighbor of these two hydrogens. Right? So we would expect potentially a complex signal here, or you add them all up, 4 neighbors with 5 peaks. Methyl here has 2 neighbors. So it definitely matches. Or in terms of carbon NMR, it also is a match because we would expect to have 2 sp2 hybridized carbons. So those would be here and here. And then 1, 2, and they're showing these as being equivalent. They're not exactly in the same chemical environment, which you can see from being separated up here in the NMR. because of one being in closer proximity to the ethyl group than the other, not allowing for free rotation. So it's a little bit weird that they're coming the same shift, but looks like they are in space, so we will go with it. So these are our sp3 carbon. In terms of the IR, this is a little bit hard to read. I would like to see sort of a 3,000 wave number mark, but it's likely that this peak off to the left here is sort of to the left of that 3,000 mark, and that's likely due to a hydrogen attached to sp2 hybridized carbon, which would match the alkene. And this is probably the carbon-carbon, which is very small and you can not see it. It's not my favorite IR, but it's that. And then just to match the mass, what we would expect, just have to do a quick calculation here. So we'd have 1, 2, 3, 4, 5, 6. 6 carbons is, let's see, 72 plus 6, 7, 8, 9, plus 12 for the hydrogens. 84. So that is the peak that we see here, and then this is a very small n plus 1, which is observable